let's talk about a material that is so common, so everywhere, we barely even notice it. And yet, it literally holds our entire world together. I'm talking about cement. It's the unsung hero of our modern infrastructure, the magic ingredient in concrete that builds our cities, our bridges, our dams, pretty much everything. But here's a thought. What if it wasn't infinite? What happens if we start to run out of the one thing we use more than any other substance on the entire planet, besides water? It's kind of a terrifying thought, right? The consequences would be absolutely massive. And believe it or not, that question isn't just some far-off hypothetical. Based on how much we're making right now, our best reserves of high-quality limestone, the essential raw ingredient, are estimated to last for only about 50 more years. Just 50 years. That startling number forces us to take a much, much closer look at how this critical material is actually made. So, how do we even start making this stuff? Well, the very first step in the process involves a massive decision. Historically, there have been two ways to go about blending the raw materials, a wet process and a dry one. And the choice between them has huge consequences for energy, efficiency, and of course, cost. So here's the trade-off. With the wet process, you add water to create this goopy slurry. The huge advantage? You get a perfectly uniform blend, which is great. The huge catch? You have to burn off every last drop of that water, which takes an incredible amount of energy. The dry process, on the other hand, just uses a powder. It's a bit harder to mix perfectly, but it's way, way more energy efficient. And when I say way more, I mean it. Look at this. The difference in energy is just staggering. The dry process uses almost half the energy of the wet process. It's no wonder that today, pretty much every single modern cement plant on the planet has gone with the dry method. It's a total game changer for efficiency. All right, now let's get to the main event, the heart of the whole operation, the rotary kiln. This thing is a monster. It's a massive, slowly rotating steel furnace, sometimes as long as a football field. It's inside this giant crucible at scorching hot temperatures that a bunch of simple raw materials are transformed into something completely new. But what is actually happening in there? You can think of it as a journey in three main stages. As the material tumbles down the kiln, first it hits the dehydration zone, where any leftover moisture gets boiled away. Then it enters the calcination zone, where the intense heat starts to break down the limestone itself. And finally, it reaches the hottest part, the clinkering zone. This is where the real chemistry happens, and the new compounds that give cement its awesome strength are forged. Okay, this is where the real magic happens, the chemistry. It's all about this super precise sequence of reactions. As the temperature climbs past 600 degrees Celsius, the clays wake up and get reactive. At 900 degrees, the limestone breaks down into lime and carbon dioxide. Around 1200 degrees, we get our first key cement compound, baelite. But the most important moment happens at 1350 degrees. Here, some of the other minerals actually melt into a liquid, acting like a chemical matchmaker, a flux, that allows the most important reaction of all to happen, the conversion of that baelite into alite, which is the compound that gives cement its incredible early strength. So you'd think, okay, the material leaves the kiln at a blistering 1450 degrees Celsius. The hard part's over, right? We cooked it. Nope, the process is far from finished. The next step, the cool down, isn't just about chilling out. It is another active and absolutely critical chemical stage. I love how one of our sources puts it, quote, "The reactions do not get completed inside the kiln." Think about that. The final properties of the cement, the stuff that really matters, aren't even locked in until after it leaves that furnace. How it cools down determines everything about its final strength and reactivity. If you mess this up, if you cool the material down too slowly, two really bad things happen. First, that super strong agalite we just made can actually revert back into the weaker baelite, basically undoing all the hard work of the kiln. And second, that liquid matchmaker stuff can form big, lazy, unreactive crystals that hurt the cement's performance. So what do? They use rapid cooling. Think of it like flash freezing, to lock those desirable high-strength compounds in place and keep all the crystals small and super reactive. All right, so we've cooked it, we've flash frozen it. What's next? Well, those cooled pebble-like nodules that come out of the cooler are called clinker. That's the intermediate product. That clinker then gets sent to a massive mill, where it's ground up with a little bit of gypsum into that fine gray powder that we all recognize as cement. But here's the thing. It's not as simple as it sounds. because you're trying to grind materials that have very different hardnesses all together in the same mill. You've got soft gypsum, which is in there to control how fast the cement sets. Then you have the hard clinker. And sometimes other additives, like slag, an industrial byproduct, can be even harder. The big challenge is to grind everything down to a perfectly uniform fineness, which is absolutely crucial for getting predictable results. So to solve this puzzle and make the incredibly energy-hungry grinding process more efficient, plants use a really clever trick, something called grinding aids. These are basically special chemicals that coat the tiny particles as they're formed and stop them from clumping back together. It's a simple addition, but it can dramatically reduce the amount of energy needed to get the job done. And you have to understand, throughout this entire complicated dance, from the moment the rock leaves the quarry to the final bag of cement, quality control is absolutely relentless. Samples are constantly being pulled and analyzed. Using high-tech methods like X-ray fluorescence, a lab can get a complete chemical breakdown of the material in under 5 minutes. This allows the operators to make tiny adjustments in real time to keep the final product perfectly on spec. So there you have it, the incredible chemistry and the massive engineering that goes into making the very backbone of our civilization. But this whole process also brings us right back to that urgent question from the beginning. Knowing our best resources are finite and knowing just how energy intensive this all is, the challenge ahead is crystal clear. Cement built the modern world. The question now is, can we reinvent it for a sustainable future?